Hi and good afternoon everybody. Many thanks for joining us today. Today we are talking about our new concrete wall design functionality, which was added to the MasterKey slab designer module, which has been renamed to MasterKey slabs and walls designer module in the MasterSeries 2023. My name is Andras Herbay. I'm the sales manager here at the MasterSeries, and as usual, I'm joined by my colleague Patrick McGinley. Before we start the presentation, I would like to quickly share some practical information about the GoToWebinar. The control panel can be hidden with the red arrow button, and questions or messages can be sent with the chat option. Feel free to type in any questions at any time during the webinar. We will answer them during the session, but we will also review the questions at the end of the webinar. As usual, this webinar is being recorded and will be posted to our channels and sent out to your email, the email address. Quickly about the agenda. At first, Patrick will give you an overview of the shear wall designs, basic design rules. After that, I will demonstrate how easy it is to design a shear wall with the new wall design module. During my presentation, I will also present the different design components and design methods. And as usual, we will finish with the Q&A section. Okay, so let me hand over the presentation to Patrick.
Thank you, Andras. I'll need to show my screen here.
Yeah,
yes, you can see. Up.
We can see your screen now.
You can see the model.
Yes,
that's good. Okay, great. Hello, everybody. Yes, my name is Patrick. I'm one of the structural engineers at MasterSeries, and today I'll just be going through a bit of background on shear walls and how they are designed traditionally, and a few other bits and pieces. So thank you, Andras. So as I say, I'll go through some of these topics on screen here today. So for some, it might be new information. Some others might serve as a refresher, but I'll be going through exporting this MasterFrame model using MasterCAD BIM, the functions of a shear wall or shear core, setting out and best practices for shear walls and cores, loads and accommodations applied, the load transfers, the structural behavior, failure mechanisms, and design methodology, both looking at traditional and using MasterSeries itself. And then we'll have a look at wall pier and coupling beam checks within MasterSeries. So if you have any questions, please do feel free to ask in the chat, or if you have any comments or feedback, we would love to hear. And then Andras is obviously going to go through an example of frame setup within MasterSeries and show how it can be designed within the Concrete Slab and Wall Design module. So I'll just start off. Well, you might notice that this model, this was used by Dr. Martin O'Gara in the previous webinar, which was an introduction to the features in the latest version of MasterSeries 2023. And we'll leave a link in the description to that video when we upload to our various social media channels. But I had quite a few queries from previous webinars about this presentation style. And it is possible for our users to replicate this as well. So I'll quickly show you how I'm doing this. I'll note that you'll need to have access to MasterCAD BIM, which is our add-on module for MasterFrame. So all I did was open the MasterSeries FE model with a MasterFrame, and under BIM Exchange menu tab, export to IFC, and then use a third-party tool, in this case it's SketchUp, to import it in and have a play about. But I'll just quickly show you how I've done that, and hopefully there'll be no hiccups. So I'll just Concrete Webinar, I'll just call that demo 3. I might have done a few others. So export IFC, so that's went into my folder, and it should be as easy as going into import and just making sure that we've got our IFC file type selected, and I think I called it IFC3. It'll be just saving up here as we speak, and this is hosted in OneDrive, so it's going to take a second, but this is one I made earlier, and it's pretty much as simple as this. So now you can use all the functionalities of what you would have in SketchUp. Now this is obviously a third-party software. You might have other preferred ones to use. I've used this in the past. It's particularly useful for client presentations and where you're communicating critical construction sequencing, for example, in temporary work. So MasterCAD can open up that functionality for you as well, and it also allows for bidirectional model exchanges with other software packages, including Revit, Tekla Structures, and AutoCAD. So if you are interested in getting a trial, it's definitely worth getting in touch, and we can activate that for you, and you can have a play about. So back to our shear wall. So a shear wall, it primarily provides lateral stability to a building, providing lateral support against horizontal loads such as wind or notional loading or equivalent horizontal forces, as you might recognize them by, and it does this by resisting shear, moment, and axial forces. Concrete shear walls are very stiff compared to other lateral stability options such as steel bracing, and are very popular on higher buildings where deflections may be critical. I've listed a few horizontal loads that are resisted by the shear walls, and they also do take vertical loads as well. So they can be designed to take all the lateral loads or in combination with the columns as a sway frame, but portalization in concrete frames isn't preferred, as it required fixed connections between elements, and therefore adds a bit more complexity to the design, construction, and installation of the frame, as well as connections between elements relative to a simple construction with pin connections and a braced wall. So if we look at the setting out of the walls, in this model we're looking at a shear core, which is typically located in the center of the building for vertical access through a set of lifts or a set of stairs. To successfully transfer the loads down to the foundation, shear walls should be set on every floor to take the lateral loads. And for the layout and plan, ideally you want them in the same location on all floors, so and not too central, and maybe have them symmetrical. So that's for shear wall. So and also it's worth noting, in some cases where uplift may be an issue, it may be an idea to relocate columns away from the wall so that the wall attracts more vertical axial load to help manage any uplift combinations. So if you have one shear core, it's good practice to have the shear core located in line with the centroid of the building, coincidental along with its center of stiffness to minimize any torsional effects. But there always will be some kind of torsion that develops from eccentric loading, which will need to be accounted for in the design of the walls. So there are plenty of examples and rules of thumb of where to best locate shear walls, but in this case I'll show the ideal location for shear walls in this building in black. So we've got two shear walls in each direction, as you kind of want that as an essential rule, and you will want them symmetrical. You want the bays far enough apart and close to the edge, and obviously in the same location at each floor. And next we'll have a wee look at our lateral loading. So most countries with low seismic risk, the most significant loads the shear walls will be resistant are wind loads. And if you're doing some simple calcs, there are some quick numbers you can do for the preliminary sizing. I particularly like the iStruct guide titled Conceptual Design of Buildings, and it gives some good outline guidance for wind loads for a quick 5-second estimate, as well as longer 10-minute guesses for, and the very common 5-second estimates would be 1 kilonewtons per meter squared standard, 1.3 for conservative, and then 1.5 kilonewtons per meter for high exposure sites. So for equivalent horizontal forces, aka notional loads, likewise, we can use some preliminary figures, and within Eurocode 1, we can take 3% of the worst case load combination for a given structure as a generic figure to be applied horizontally at each floor. But more in-depth calculations in the Eurocode gets more specific about the application of loads on both steel and concrete frame buildings. So again, the iStruct has a good bite-sized technical note covering equivalent horizontal forces as well. So I'm going to just pull up some of these references I'm making here as well, as I like to do. So this was the conceptual design of buildings from the iStruct. So definitely worth having a read through of those to give yourself a good idea of where to set up your shear walls. And then this was a notional loading technical guidance note for your equivalent horizontal forces. These lateral forces can be dealt within MasterSeries, and using our MasterKey wind loading module, we can obtain all the relevant pressures and Q values for British and Irish locations, and then MasterFrame allows you to generate the wind panels and apply the loading, as well as allowing you to specify the percentage of the factored vertical loads in any loading case to add them as a horizontal notional load to your model. So that can all be done within MasterFrames. I've listed a few loading combinations that are commonly critical in the ULS design of both equilibrium and structural strength design, which can all be automatically generated within the MasterFrame load generator. But any good engineer should have a think about which cases you would consider critical for the different design conditions, and we can go through a couple of those later. So it's good to identify the transfer of loads that will take place in buildings, and in this case we're looking at wind loads here. So where wind meets the building through the external cladding spanning between floors, and in this case the floor has been modelled as a surface within the MasterFrame using the Finite Element Analysis add-on. So to differentiate between the different elements, we have the finite element surfaces such as the walls shown in blue, the floors shown in green, and then we've got our individual elements which will be modelled in MasterFrame, such as the concrete columns and beams, which are in grey, so our ground beams down there. And then we've got also shown in grey the pile caps, which will be carried out, their design will be carried out in the MasterKey pile cap designer. So I'll note that the pile cap designer goes up to 9 piles. So in this case, we would need to model a shear core pile cap as an FE surface and then design that separately. But back to the load transfer. So the floor will act as a diaphragm, which effectively is a stiff plate which can transfer the wind loads back onto the shear core. In this case, we have an in-situ floor, but diaphragms can be assumed when using one of many other element types, such as precast, concrete planks, or biscuits, metal decks, as long as they have the required in-situ topping. Steel floor arrangements using deep metal decks or purlins typically require plan bracing to do the same job as a concrete deck and acting as a diaphragm. So all of these elements are required to work together in order to transfer horizontal loads back to the ground in a safe manner. So to recap, if we look at the modules on the left-hand side, all of our model setup and analysis is done within MasterFrame and our Finite Element Analysis add-on module. Then all that analysis and model information generated is passed into our design modules to design the individual elements, for example, our beams, columns, and pile caps. And of course, Andras will be focusing on the MasterKey Concrete Slab and Wall Design module in a little bit, which has the ability to design this floor as well as the shear walls. We did do a previous webinar on the topic of finite element analysis, modeling, and the concrete slab designer back in March, which goes into detail and best practices for modeling and designing a concrete floor using these two modules. So again, we'll put that link up as well for you to have a look. So the load is transferred onto the shear wall as a series of point loads, really. But one way of simplifying the understanding of the design of a shear core subject to lateral loads would be to visualize a fixed cantilever hollow section with a varying distributed load with some eccentricities plus an axial load here. And so the section would need to be designed for shear moments and whatever torsion is just from the eccentricities. And if you wanted to complete the comparison, the bolts are the piles and the base plate the pile cap, so they also would need to be designed to resist the applied forces. So if we look at the failure mechanisms of a concrete shear core or shear walls, we can have a look at some of the critical global failure mechanisms here. And we've got our vertical and horizontal shear failure mechanisms, which will require sufficient reinforcement in each directions. The stresses induced from the moments onto the base will create a push-pull effect on either side, and it will require sufficient reinforcement and or concrete to deal with these stresses. This check is typically the most critical, and we'll go through a short preliminary design stage check for early stage designs next. Consideration will also need to be given for buckling, as well as especially for slender walls, and also when we introduce openings, we will need to consider the design of our coupling beams, which will have the job of sharing the horizontal load between the two vertical piers. So for early stage design checks, as I mentioned previously, bending can be critical for the design of shear walls. So a simple but conservative process would have been used to calculate the maximum and minimized localized stresses at the base of the wall to determine the reinforcement required and to check the reinforced concrete there. So I'll start with a caveat. We are checking a single wall panel here, but really the shear wall we're looking at is part of a shear core, and it will behave more like the hollow section I showed earlier. And the correct procedure in this case would be to take the shear core as a whole, working out its section properties and determine its resistance from that. But for simplicity's sake, we will treat it as a single shear wall. So I won't be taking any values in this here to save a bit of time and possibly confusion. So, but starting out with our free body diagram of a simple fixed base cantilever, we can take the total factored wind load applied to the side of the building as a UDL and get the moment at the base of the wall using WL squared over 2. And in this example, we can then work out the total factored axial load as well, coming down onto the wall. And as I mentioned previously, we can use our engineering judgment to go through the different load combinations to determine which combinations are critical to the various elements. For example, we may want to take live loads as 0, so we can design for worst case tension, as obviously including our live load will help restore any uplift forces. So we can then work out our maximum minimum applied stresses, combined stresses on the base by using this equation, which is taking our axial force over the area and our plus or minus our moments over the area as well. So the reinforcement can then be determined using a column design methodology where minor axis bending as well as axial stresses just worked out from the global major axis bending and axial forces is applied. So again, I'm going to reference another I/D note here, and this is called the design of reinforced concrete walls, which is very relevant. So that goes through like a simple that simple check that I'm basically going through here now. So worth checking that out as well. So with this traditional design check, walls can be designed fairly conservatively, but with the FE modeling, we can get so much more accuracy on the application of the loads and the analysis of the wall, as well as the incorporation of the concrete wall design module now as well, to be able to separate and manage each of the wall piers and carry out some sensible rationalization of the wall at each level. So I've outlined a few advantages here, but I'm sure you will appreciate the major advantages of carrying out the design within the software and the huge economical benefits using the finite element software in combination with the wall design module and what that can bring. So just to go on to a little bit of geometry, typical geometry of a wall. So there's some rules of thumb to follow for the height to breadth ratio here, and typically The height to breadth ratio is between 15 and 30. And just so we get an idea, this wall I think is about a height to breadth ratio of about height over 20. That's a 40 or 4 meter high wall. It's about 200 mil thick. So a minimum thickness of around 150 can be specified, but generally 200 to 250 is used. That helps avoid problems on site with some compaction and reinforcement congestion and detailing, as well as you've got fire resistance requirements there as well. So the Eurocode sets out some rules for what defines a short or shear wall based on the height to width ratios. So greater than 4:1 being slender and less than 1:1 being short. When a wall is slender, its axial plus bending resistance is reduced, and typically bending is dominant, and it's vulnerable to buckling failures, whereas with short walls, it's shear that's dominant, and in between you have a combination of both shear and buckling. So finally, a little bit about the restraint conditions of the wall. So within MasterSeries, you'll need to manually input for each of the wall panels that you're designing, which Andras might get into a little bit later. But to use this wall as an example, the wall that we're using won't automatically assume restraint from the internal wall. So it's something you'll need to manually input, whether it's restrained on all four edges or just at the top and bottom, or whether it's even a cantilever wall. So that's very important to input into the design module. And so one of the other key inputs into the design software will be this Pier subdivision settings. So the example we took earlier used 1 meter strips at the end of the wall to get the worst case stresses. And within MasterSeries, we have multiple options for dealing with the subdivision of piers. So we can say, we can specify fixed width, say 1 meter starting from the ends, and then it'll make up the difference in the middle there. Or we can divide the wall into a certain number of equal strips. So in this case, we have 4 equal strips, and it'll divide them out equally. For both the fixed width and equal strips, the strip dimensions can be optionally rounded up or down, taking into account the reinforcement bar locations. These first two will likely be the most commonly used, but we also have the option of specifying unequal strips. So whichever way you like, by inputting the exact length of strips for what we want for each within the software. And then we can either choose 2 zones, or left and right zones, or else a 1 zone, which I like for getting visual outputs for the total moment or forces acting on a panel or either side. But the smaller strips are more ideal for reinforcement. We can now look at how MasterSeries goes about the design of each of the individual strips. So in this case, I'm actually showing 5 equal strips here. So we've got our global actions on the wall. We've got our global major axis bending, or vertical axial forces. So, and then we've got horizontal forces on both directions, and then some global torsion and some nominal eccentricities. And if we explode this up, we can then look at each of these as individual strips, with their global loads being distributed or allocated across each of the strips accordingly. MasterSeries then can carry out the design for each strip, taking into account all the above, and the breakdown of these checks is denoted quite clearly on the design output. Again, it's worth paying attention to the restraint conditions for each panel, as this will be another manual entry, critical for your design. So I've mentioned about coupling beams earlier. I'll jump back into the failure mechanism slide so you can see the deflected shape on that last diagram with the opening. So here, the coupling beam behaves as a fixed beam, so transfer moments, much like a sway frame, but also axial loads to distribute horizontal forces between the vertical piers. And finally, there's quite a bit of vertical shear stress that is induced within the wall when it deflects, and you can see this from the first diagram here. And due to the openings, then these forces will be concentrated at the location of the coupling beam. So there can be some quite significant shear forces introduced into these beams. You may have seen diagonally reinforced concrete coupling beams, which are mainly used in high seismic risk zones, although MasterSeries considers a conventional reinforced concrete coupling beam as it is the most extensively used coupling beam type in the building design in low risk seismic zones. And finally, for deep beams where the length over the depth is greater than 2, a strutting tie check is carried out for the design of the beam. And for a length over depth smaller than 2, we use standard beam theory. So that was just a bit of an overview on the shear wall and their behaviour. Hopefully these slides have been useful in helping you understand the behaviour and design approach to shear walls. I find value in trying to explain them to you, so I'm grateful of your time and hope you've learned something new today. So I'll just note that I wouldn't be referencing this reinforcement slide either because I never got to finish off the detail on it. But as I say, if you have any other feedback or comments on what we've talked about, we would love to hear it. And Andras, I'm going to hand back to you to demonstrate the software for us. Thank you.
Thank you, Patrick. Just gonna share my screen. I hope you can see my screen. Okay. So, thank you, Patrick. Let's go straight in the MasterFrame. So here we have a small multi-story building. So this is the model we used to introduce our MasterKey Concrete Slab Designer module back in 2020. Back then, we presented how you can define and check your basic reinforcement, additional reinforcement, punching shear reinforcement as well. However, in the MasterSeries 2023, we extended the capabilities of this module, and we added the shear wall design. And now, hopefully, we'll be able to finish this model and design the concrete walls as well. Okay, I'm gonna close the slab reinforcement, and yeah. So the new functionality, the shear wall design module includes design components for concrete wall piers, a column-like design, and wall copper beam design for below and above openings. So before we go and do the design of the wall, let's have a quick look at the model and the loading. So this is a nice finite element multi-story building with concrete slabs and walls. The walls are 200 mil thick and 25-30 concrete walls, and we have 2 door openings in the wall on grid line D. Because we want to design the walls, that's why we have to ensure that we use codified concrete materials. Let's have a quick look at the loadings. Okay. So we have minus 0.5 kilonewton per square meter full area loading dead load on both levels. We have minus 3 kilonewton per square meter live on level 1 and minus 2.5 kilonewton per square meter live on the roof. And we have minus 1 kilonewton per square meter partitions on each levels. And of course, I have I applied the wind loading in the plus X and the plus Z direction. So here you can see the generated wind loads in the plus X and the plus Z direction. The yellow represents the pressure, the wind pressure, and the green represents the sanction. Okay, let's just quickly check the analysis result to see if our model works as expected. Okay, shell elements, of course, and yes, Y displacement. So this is our Y displacement. So for me, it looks good. So this is our vertical displacement, and this is our horizontal displacement in the X direction and the Z direction. So it looks good. Okay, let's go and design the concrete walls. So under the main design menu, now we have a new functionality called Concrete Wall Design. Okay, the first things that appears is the basic data and defaults. We can set our steel grade and cover. I'm gonna use the default default settings now, and we can set the basic bar sizes, spacings, design methodology for the shear walls, and of course the same thing for coupler beams as well. You can save it. You can save your defaults. So these are the usual MasterSeries functionalities. Okay, so I'm gonna use the default settings. So this is the interface of the concrete wall design, quite similar to the concrete slab designer. So we have object list for piers, coupler beams, and we can switch between those. Okay, so let's generate our first pier zone. But before we move on, I'm gonna filter for the wall surfaces using the U filters option. So let's filter. Let's show the FE surface only and vertical. Okay. So yes, with the plus button, we can add a new object to the object list. And first, we have to select and first we have to select the finite element surface that zone is going to be a part of. And then we can draw the position of the zone into it. So we have two options to draw the zone. So using the draw x1, x2, y1, y2, we have to select the horizontal and the vertical start and end points of the zone, or we can use the draw rectangle option. In this case, we only need to draw a diagonal of the zone. Now I'm gonna use this. So in draw mode, I'm gonna select the bottom left point and the bottom and then the top right point of the zone. Okay, so the wall piers a column-like design, designing the vertical components with the various bending and shear. And if you turn on the drawing, then we will see. So we can see that the wall pier is already divided into design strips, which will be discussed a little later. So before we go on, move on, let's have a quick look at our inputs. So here under the object list, so here we have our input area. So under the geometry, you can see the position parameters of the zone, which can be altered. So with the first option, we can anchor the zone to a node. We can modify the horizontal and vertical placement of the zone. However, we can do this with the snap points as well on the graphic. So by dragging the side, the middle side snap points, we can alter the size of the zone. But we can perform the same with the parameters. So we can change the start coordinates. The horizontal placement of the zone is in local coordinate system. So we can modify the start point, end point. For vertical placement, we have two options. By default, the program uses the local coordinate placement, but if you want, you can change the global coordinate, or even you can use or you can position the zone vertically between two levels, even with offset from levels as well. Okay. Move on. The next is the design method. So design method is the most important is the most important area. The design method of the Pier subdivision that you choose here might affect the accuracy of your design. So by default, the program uses the equal strips with fixed width design method. This method split up the zone into 1 meter width. This method splits the zone into equal width strips, starting from the left and right with a makeup middle zone. Of course, the default pier width of 1 meter can be changed here and in the default settings as well. In the graphical drawing, you can see the actual strips. As we can see that even though we selected 1 meter with fixed strips, the outer strips are slightly narrower, while the innermost strips are somewhat wider than 1 meter. And this is because the program chooses sensible design strip width with the rounding to rebar bar spacing midpoints. And on the graphic, we can see the various design forces on each design strips. Now we are watching the axial forces. Axial forces on each design strips from the critical load case, but under the drawing options, just move this up. So under the drawing options, using the critical load case force drop down menu, we can switch between the different design forces. So we can display axial, shear, major and minor, moment, major and minor. And we can turn on and off the min-max values, and of course we can hide the forces by removing the tick from the draw option. But of course we have other design methods as well. So as Patrick mentioned, we have the equal number of strips option. It works similarly to the equal strips fixed width method, but in this case, the wall pier is divided into the given number of the strips. We have the user defined strip width method. With the user defined strip method, we can enter strip width values from left to right, separated by semicolons, and the program makes up the last strip width. In this case, in the case of this method, you have to aim to enter width that match the specified rebar spacing midpoints, as we do not have the strip width rounding function with user-defined strips. Okay, we do also have the one-zone design, as Patrick mentioned, which takes everything as one zone. This method is appropriate if the aspect ratio is smaller than 6 by default. This is not the case in this case, so we can see a note in the detailed design here saying using the one zone method is not a good idea. However, this is useful to see. The major the major moment, which is 411 kilonewton meter, and this is our axial force. Okay, and then the last design method is the left and right zone axial end bending. The left and right zone method splits up the wall zone into 3 strips, 2 outer zones and 1 inner zone. Only the outer zone carry the moment, and the center zone designed to shear forces only. The width of the outer zone can be entered as a can be fixed, or can be defined as a multiple of the wall thickness, or also there is an option to auto size the zone width as well. Okay, so these are the methods. So let's switch back to equal strips fixed width method, and split up the wall into strips, which gives more accurate design in this case, because this method is able to pick up the variability of the forces across the wall. Okay, so these were the design methods. Let's move on. Looking at the bars, we have got the same bars throughout. So we can draw the bars on the model with the rebar to draw option. So under the drawing options, we have a rebar to draw option. So you can see the horizontal rebars. You can see it's 16ths at 200. Sorry, the vertical rebars 16ths at 200, and this is our horizontal rebars, which is 10ths at 200. Okay, so now we have same bars, all strips, which might be sensible, but if you do want to use different bars per strips, you can separate the input to specifying different arrangement of reinforcement per strips. So for example, we can say that in the first strip we had we have 20 and 200, and this is our first strip, 20 at 200 on it, and this is our default. And the rest of the wall is on default vertical reinforcement 16 and 200. Here you can see in the color legend. Okay, I'm gonna set back to use the same rebars in all strips instead. Okay. And the last input option is the setting of the edge restraints. So by default, the wall zones are designed as pinned at the top and the bottom edges, but there is an option to design them as top and bottom pinned and one vertical edge restrained, or all four edges restrained, or we can enter custom beta value as well, or there is an option to design them as a cantilever. So these are the edge conditions, and we can also fix the top and bottom edges rotationally, and there is an option to override the wall height for slenderness and buckling calculation. Okay, so these were the input option. So now let's take a look at the detailed design. So this is our critical load case, and as you can see, the slenderness of the wall, the slender moments that have been calculated for the wall along with the nominal eccentricities. The design capacity is checked with a fully numerical biaxial bending moment with full shear forces, and the detailing checks are also done. So the program checks the max-min areas of rebars and spacings as well, and of course that continues for all the other strips. So in this design we have strips, 6 strips, so we can see the design of all the strips for each other. Okay, so moving on to our wall coupler beams. So by clicking on the coupler beams here, we can create a new, we can add a new object. So the coupler beams link piers together and transfer the moments between the piers. So now I'm gonna add a wall coupler beam just above this door opening between these wall piers. The placement method is the same as we saw with the wall zones. So we only need just to click on by clicking on the plus button, we can add a new object to the list. And first, we have to select the FE surface, and using the draw option, we can easily draw the zone itself. Okay, so now it's created. So as Patrick mentioned, if the L over D is less than 2 by default, the program does a strut and tie check. However, in this case, as you can see here under the design method, the compression tension force couple was not found for strut and tie method. so the program intelligently switched back to standard beam theory. If it used the Strat tie check, we would see the compression node design, the Strat design with the transverse brusting check, which takes account of all horizontal and vertical rebars, and obviously the tie check with that as well. In the input area, under the design method, we have some design options for the coupler beam. So we can decide whether we want to use compression bars in the design. So if you decide to use them, we must provide the proper links to the bars. And in case of Strat and tie design, we can define the projection of the Strat and tie model into the wall as a multiple of wall thickness. Okay, and yeah, looking at the bars, we can see we can set the top and bottom bars, side bars, and the shear bars, of course. So now I'm just gonna delete all these created piers these created piers and coupler beams. And I'm gonna show you how you can save time by auto-generating all the zones rather than doing them manually. So we have got an auto-generate wall zone function, which quickly creates the zones with some controls in all the selected wall surfaces. So first we have to select all the appropriate wall surfaces that we want these zones to be created on, and then push generate. Okay, it's ready. So as we can see, the program created all the wall pier zones and coupler beam zones. So we have 8 wall pier zones and 2 coupler beam zones. The green zones, sorry, yes, without the reinforcement. So the green zones, green outline zones are the wall pier zones, and the blue outline zones are the coupler beams. So let's draw the reinforcement for all the generated zones. So we can see all the zones have the default arrangement of bars that we have specified or accepted in the design default. So 16s at 200 for vertical and 10s at 200 for horizontal. So this is what we can see. So this is our vertical reinforcement, 16s at 200 and 10s at 200 for the shear walls, and 2 number of 10s for top and bottom for the coupler beams, plus 2 number of 10s sidebars, and we have 2 number of 10s legs at 200 for shear reinforcement in the coupler beams. We can look at the unity ratio for the current reinforcement. We have several options, so we can see both the axial with moment for shears, shear major or Strat unity, or we can see the maximum unity ratio. as well. So as we can see, all the wall works with the default reinforcement arrangement. So let's do some optimization now. Of course, we can do some manual design, so you can change the reinforcement and find the optimal solution, or we can do some auto design. So here in the middle of the right hand side panel, we have an auto design area. So with the selected button, you can perform auto design just for the selected element, or with the all sets option, you can design all the elements in the current type, pier or coupling beam, or with the all button, you can design all the piers and coupling beams in one go. So this is what we are going to do now. So the program now going through all the piers and coupler beams and design cases and selecting the critical one for design. So now that's now being optimized. And in the auto design menu, we have an option to scan for failure. The scan for failure to see if any of the wall zones are failing. But thankfully, no design failures have been found. So watching the maximum unity ratio, we can see we can also see visually that all the wall and the coupler beams work. So let's take a look at the applied reinforcement. So let's switch to vertical first. So this is our vertical reinforcement. So we can see that it went down from the default 16s at 200 to 10s at 350. This is the minimum reinforcement. So yeah. So the detailing check define the amount of the necessary reinforcement in the wall. And if you switch to horizontal, then we can see that you've got the same horizontal bars for all the walls, which is 10s at 300. And the coupler beams have 3 number of 10s tops and bottom bars, and 2 number of 10s sidebars. And the shear reinforcement is 2 number of 10 mil legs at 400. Okay, so this is the optimized reinforcement. That is a useful trick. So we are able to multi-select objects by holding the control button and selecting the objects on the graphics, or in the object list as well, or we can also window them. In multi-select, you can quickly make, for example, you can quickly make, for example, reinforcement for the same for the selected object to have some commonality. So, for example, you can change the reinforcement for the selected walls, vertical reinforcement to 10s at 300, for example. Yes. Okay. So yeah, so let's say it's ready. So we can do design reports, of course, or we can also export the reinforcement to a DXF or DVG AutoCAD drawing representing the design intent. So under the output, we only need just to click on export. We have to select. We can select which surface we want to export and which rebar type we want to include in the drawing. And yeah, export. Okay, I have already opened an AutoCAD file, and let's open the file. Yes. So this is our drawing. So the design layout show what areas are attracting what quantities of rebar in terms of diameter, spacing for both vertical rebar and horizontal rebars. Vertical rebar and horizontal rebars. Yes. Okay. So that's our new concrete finite element wall design function, which was added to the MasterKey slab designer module in the MasterSeries 2023. So for those who already have the slab designer module, this new shear wall designer is already there and ready to use within the MasterSeries 2023. Okay, so ladies and gentlemen, I would like to thank everyone to attending today. I hope you enjoyed and learned in this presentation, and see you on our next webinar. So if you have any further question, you can get in touch with us on our usual channel. So you can send an email if you want. If you want to try out the software, just go to the MasterSeries website and fill in the request form to do so. After the webinar, please do not forget to fill in the short 1-minute survey to let us know how you like the webinar. Okay, so ladies and gentlemen, thank you very much for attending, and have a good day.